This video will review some of the basic ODEs you learned about in Math 312. We will look at linear first and second order ODEs and their solutions. To see how these solutions are obtained, I suggest you look at section 4.2 or your notes from 312. First, we're going to examine the difference between an initial value problem, or an IVP, and a boundary value problem, or a BVP. Both of these define a differential equation in addition to certain conditions that are needed to obtain a unique solution. The difference between these two problem types is the form that those extra conditions take. For an initial value problem, the conditions are given at a single value of the independent variable, usually at 0. If multiple conditions are needed, for instance for higher order differential equations, then the conditions are set on higher order derivatives at that single value of the independent variable. Often initial value problems correspond to an independent variable that is in some way temporal or time. So here we have an example where the function at 0 and the derivative of the function at 0 is assigned. For a boundary value problem, the conditions are given at more than one value of the independent variable, often at the extremes of the domain of the problem. Boundary value problems usually correspond to an independent variable that is related to space, not time. And so here we see an example where the function is defined at x equals 0 and at x equals 5. First, we're going to consider a first-order linear ODE with constant coefficients. This ODE is probably the simplest one that you will ever see. It has one initial condition at t equals 0. Lambda is a constant real value, and the initial value is some constant y naught. The solution to this problem is y naught times e raised to the lambda t. And this works for any constant lambda or y naught. This is definitely a good differential equation to remember, as these problems show up surprisingly often for their simplicity. This second order linear ODE corresponds to a large class of ODEs that represents a wide variety of physical situations. This ODE can be associated with either initial or boundary conditions, and we will actually see it used with both types of conditions. It is assumed that a, b, and c here in this differential equation are all constant real values. The general solution is given here as the sum of two functions, and those forms of those functions we will discuss on the next slide. The values of C1 and C2 are determined through the initial or boundary conditions that are given in the problem. We'll see an example of how those values can be found. The values of R1 and R2 are found by solving the characteristic equation given here, this quadratic equation. This can be solved using typical techniques of factoring or just the quadratic formula. There are three classes of solutions that can come from this second order ODE, and it depends on the values of R1 and R2. First, if R1 and R2 are different but real, then the solution is going to be a sum of two exponentials, where the exponential is e raised to the R1t and e raised to the R2t. If both R1 and R2 are the same value, then we multiply that second exponential by a t in order to get two separate functions. And finally, if R1 and R2 are complex, then just by the theory of quadratic equations, we know that they will look like this. They will be some real value alpha plus or minus I times some real value beta. And this comes directly from the quadratic formula. We can then write the solution as this following combination of exponentials and sines and cosine functions. And this last one is what is going to show up most often in our work. But really, understanding all three of these classes of solutions is going to be important. So next, let's look at an example. This ODE is a boundary value problem with conditions given for the solution at the point x equals 0 and x equals pi over 2. First, we solve the characteristic equation to see that R1 and R2 are complex and have a real part of 0 and an imaginary part of 5/3. Using the formula above, we will get the following general solution to this ODE. So next, what we have to do is determine the values for C1 and C2. To determine those values, we use the boundary conditions. So first, when we set x equal to 0, we see that y of 0 should be 1. So plugging x equals 0 into the solution, we see that we simply get C2. The sign goes away, and the cosine becomes 1. Therefore, C2 has to equal 1. For the second condition, we plug in x equals pi over 2 to the solution, and we end up getting C1 times sine of 5/3 times pi over 2. And this has to equal 2. Doing some quick manipulation and solving for C1, and using some of the unit circle stuff that we know and love, we get that C1 is equal to square root of 3 plus 4. Putting all of this together, we obtain the final solution to the boundary value problem. Note that even though this is a boundary value problem, the procedure was almost identical to what was done in 312 for initial value problems.